So let's start again this session. And so the talk was made by Sophie Hecht from Imperial College, and former student of the Imperial. Okay, and you will talk about incompressible limits of a mechanical model of tissue growth. Okay, tissue growth. Thank you.
So first I would like to thank the organizer to let me the opportunity to speak today. And I'm going to present you one of the projects of my PhD. And what I'm doing is developing model for epithelial growth, so tissue growth basically. And today I'm going to present you a project where we make the link between two different kind of model. One is a mechanical model and the other one is free boundary model. So in biology there is a question which is mainly asked, and they try to understand how tissue know that they have reached their final growth, their final size, and then how do they stop the growth? How do cells decide to stop to divide? This is a major question. For example, if you see in some animal, lizard for example, if you cut their tail, it's going to start regrowing until the exact same size. So how do they know this size is the good one? That's the question. And so the biologists I'm working with are at the Francis Crick Institute, and they're working on the imaginalis of Drosophila, which is a tissue in the embryo of the fly, and which is becoming the wing of the fly. And it's a tissue which is growing really fast, so it goes from 30 cells to 1,000 of cells in few days, so that's why they focus on this tissue. And in this tissue in particular, there is two main hypotheses for the regulator of growth. One is morphogen diffusion, this one. So this is the diffusion of a chemical in the tissue, and at some point they think that if this chemical reaches some cell, then the cells are going to know that they have to stop dividing. Another regulator could be mechanical forces, so like compression or stretching of cells. So if a cell is compressed too much, then it's not going to have space to divide, and it's going to stop the growth of the tissue. So here in this project, I'm going to focus on mechanical forces. And on this tissue, they made some study. They took a tissue which have end growing, so it's at this as finite shape. Then they extract some cell and they put it somewhere else, and they start dividing again. So this shows that this mechanism is something global to the tissue. So we are going to focus here on a macroscopic model, so continuous model. So just to talk to you a bit more of the project I'm focusing on, the imaginalis of Drosophila is kind of a particular tissue because it's dividing in two parts here. You have the pouch cell, and then these cells are surrounded by the hinge cells. And these two kinds of cells are genetically distinct, so they don't mix. So this gives a sort of a structure to the tissue. And then one of the hypotheses for the growth regulator is that the inner cells are growing faster than the outer cell. So this will create some compression on the pouch cell, and it will create some stretching on the outer cell. And they think that this stretching is help the proliferation of cells, and that the compression, when it reaches some threshold, then it's going to stop the growth of the tissue. So this is one of the main hypotheses, but the fact is when they try to look in the tissue if we really have different growth rates, this is not obvious. So this is where starts my project. We've decided to make a model where we can see if even with the same growth rate, we can still observe this kind of behavior. So I told you we were going to focus on macroscopic model. And in this, there is two distinct kinds of model. One is mechanical model, where you consider a density of cell, and you basically having a PDE will tell you how the density of cell is going to evolve. So either with diffusion or transport of any term we want. And this is mainly used in tumor growth, to describe tumor growth. So this is two examples of model. And then you also have free boundary model. So here you're going to consider a domain, and you know you're going to make this domain, the boundary of the domain evolve according to some rule. So this is a less well-known kind of model. So you have some example, for example, here, and so it's less studies, and in terms of numerical simulation, it's a bit more difficult to do. But in the other one, with this model, you really have a tissue we evolve, and you can take in consideration the shape of the tissue, which is interesting. So what I'm interested in is making the link between these two kinds of models. So this has been made by Pertam, Curious, and Vasquez here. They've shown that at the limit of, in the pressure parameter, you go from a mechanical model toward a free boundary model. So what I'm going to present you today is separated in two things. So first I'm going to present you a model with a single population of cells, which prevent overlapping between the cells. And then we're going to show that this model at the limit is converging toward a free boundary model. And then I'm going to present you a model with two populations of cells, which avoid mixing. And then we are going to see what could be the limit for this kind of model, and I'm going to show you some numerical simulation. So the model with a single population of cells have been made it's a joint work with Nicolas Vauchelet, which is working in Paris 13. And so for this, we're using a model which has been developed for tumor growth at the beginning. So you consider a density of cell, the velocity v, and the pressure p, and you have a growth function. The growth function is just a function decreasing, and which cancels in one point. And then you say that the evolution of the density is driven by divergence of n times the velocity. So you diffuse in space according to with the velocity v, and then you have the growth term. So which depend to the function g depend of the pressure. So it means that the more you're going to have pressure, the less you're going to grow. Okay, and then we make the link between the velocity and the pressure thanks to the Darcy law. Here, so you say that the velocity is equal to minus gradient of p, and we also say that the pressure is an increasing function of the density. Yes. So in the paper I told you 2 slides before of Pertam, Curious, and Vasquez, the choice of the pressure was this one. So gamma over gamma minus 1 of n to the power gamma minus 1. So this is a common choice of pressure for this kind of model. And it's a nice choice of pressure because when you insert this expression in the equation, you get back to the porous medium equation, which is a really well-known study equation. So you know a lot of things on it. Yes?
Tissue is
well, the tissue diffuses because you have more cell. The tissue is growing, so it evolved in space. So you diffuse. But when you have one cell, it divides, and it pushes the other. Yeah. So this is the choice of pressure that we're usually doing. But here, you're supposed to have a maximal packing density, which in this case is n equal to 1. And this is the plot of the density at the time t in space. And you can see that it doesn't prevent actually the density to be below 1, which is kind of not good because, I mean, biologically, you can't go over this maximal density because it means that you have packing between the overlapping between the cells. So what we've decided to do is just to modify the energy and to see if we can find the same result as them, so showing that we can converge toward a free boundary model even if we have a different pressure law. Sorry. So here is the expression of the pressure that we've chosen. So it's n over 1 minus n, and we multiply it by a parameter epsilon. So here is a plot of the density at the precise time, and I mean it's obvious from the expression of the pressure that you're going to stay below 1. Now I told you that we were going to the limit, so the limit of what? With this pressure, we are going to the limit for gamma is going to infinity. If you look at the graph of the pressure here, you're going to see that when gamma is going to infinity, so let's say this is
gamma?
What?
What is gamma?
Gamma is this parameter here.
What's
sorry.
What's the physical meaning of that?
So we just say that P is the pressure in increasing pressure of the density. Just mean if gamma increases, it just means that you're increasing faster. There is no physical meaning to choose this kind of pressure. So if you take 0, 1, you see that when gamma is going to increase, you're going to become stiffer and stiffer in 1. And this is what is giving the free boundary graph at the end, because it's going to tell us that either the density is going to be equal to 0, either the density is going to be equal to a finite value. And here, with our new pressure, the parameter epsilon is going to 0, and we observe the same kind of dynamic for the pressure law. So there's few things that we can remark with this model. So we can compute the pressure equation. So you take the density equation, you multiply by the derivative of the pressure, and you get this equation. So here you see that if you multiply it by epsilon, and you make epsilon goes to 0, you're going to stay with the term p squared times Laplacian of p equal p squared times g of p. Okay? So this is going to give you at the limit the equation of the pressure inside your domain. And then you can also see that the cell density can be, the density equation can be rewritten under this form, where you have Laplacian of h, and h is this function. And this is going to be nice for the proof of the convergence. So then before actually giving you the result of convergence, we're just doing some assumption. So we have the growth function. As I told you, we consider it as a decreasing function of the pressure, and we consider that it cancels in one point. And we also consider it's bounded. Okay, so this is not a big assumption, because you just consider that when the pressure is going to be high, then you're going to start to grow less, and then at some point, if you reach a pressure, you're going to stop growing, and even if you go above this pressure, you could start having cell could start to die. Okay, and then we make some assumption of the initial density and initial pressure. So you want to stay non-negative. You want the pressure to be below the maximum pressure authorized by the growth function, and then you have some L1 estimate, which are not big assumptions. So then the main result is this one. So if you have n and p, which are solution of the equation, you can show that the density and the pressure converge strongly in L1, and that the limit of these are in BV, and then you keep the estimate, the L infinity estimate that you have. This is the equation of the pressure, the equation of the density that I've just showed you 2 slides before at the limit. Then you also say that you're having this result, which gives you the free boundary domain. From this you can define the domain. And then you have the equation of the pressure inside the domain. So just to resume in a small drawing, you have a domain here, where inside the density is equal to 1, outside the density is equal to 0, and then inside the pressure is following minus Laplacian of p is equal to g of p, and you also know that the velocity of the boundary is going to be minus Laplacian of p. Okay, so I don't have time to present you the full proof of this, but you can find it in this paper. And just to give you an idea, the first thing to do is to find a priori estimates. So you basically show that you have a comparison principle, then you're able to find that you have non-negativity of the density, you find some L infinity bond on the pressure, so and the density too, and then you show that you have L1 bond for the density and also for the pressure, and you can show the same for their first derivative in time and in space. So then from this you can show that you have convergence in L1 lock, and if you want to go to, you can go to a global convergence if you show that you have some control of the tail. And then, so you can go to the limit in this small expression. So this is just saying that p is equal to epsilon n over 1 minus n. And then you pass to the limit, so this allows you to define your domain, where you're going to have your density equal to 1. And yeah, then the complementary relations, it's the equation of the pressure. It's a bit of the tricky part, but I don't have time to explain here. But I will be happy to discuss it later if you want. Okay, so that was for the one species model. Now I'm going to tell you about the 2 species model. So this is a work done with Pierre Degon, Jean-Paul Vincent. This Pierre Degon and Jean-Paul Vincent are my 2 PhD supervisors. I forgot to tell it at the beginning. And we've also worked with Alina Chertok, and Alina Chertok. So if you look at the model with one species, you can see that it derived from the free energy according to the Wasserstein matrix. So here you just have capital P, which is a primitive of small p. And we think it's a nice property to have a model we derive from a gradient flow, because then you know that you minimize the gradient flow over the trajectory if you don't have growth term, of course. And so we try just to use this free energy and to modify it so we can get the model for 2 species. So what we did is that we kept the first term, but now we apply it to the total density. So N1 and N2 are 2 new density. So we apply capital P to the total density. Then we add a new term, which with this Q is called the repulsion pressure. So it's applied to N1 times N2. So if you look, capital Q is the primitive of small q, and the expression of small q is this one, m over m minus 1 times 1 plus r to the power m minus 1. So this tells you that if n1 times n2 is big, then q is going to be even bigger. And since you want to decrease the free energy in time, then you're going to have, the model is going to make insert that the product R goes to 0. So this is the segregation. And then in addition, we add a fourth order term to the equations, this term. So we want to penalize the gradient of each species. So we are sure that all species prefer to stay in one domain. It's not going to split in a lot of subdomains. Okay, and there is a parameter alpha here, which, okay, if you consider that you don't have this third term, you're going to have segregation at the end. But since we've added this term, we're going to have a bit of overlapping between the species at the interface and the interface between the two species. And this, the size of this interface is determined by the parameter alpha. So the smaller alpha is going to be, the less overlapping you're going to have.
What's the reason for this equation 9?
For the pressure expression, the pressure law? Well, we're just trying to make insert that we want that if R is big, Q is big, because we want to reduce. So it's just an increasing function in R, and then we have a parameter M, which determines how big it's going to be. And then M, what we want to do is making M going to the limit. But you need to have something, maybe not of this exact form, but we need to have a function which is increasing and which is have this kind of shape if we want to be able to go to the limit and to find a free boundary model.
And to provide, don't you assume an arbitrary function and you just specify the properties that you want and you prove it for all functions of this kind instead of...
Yeah, but this will be way more difficult. I mean, it could be, I mean...
The polynomial.
Well, not necessarily a polynomial, because the function that we took for the pressure P is not polynomial at all. But we need to have something which have this kind of behavior. But maybe we could do it for a generic function, like putting some assumptions so we are...
You just write down the properties that you need for the function, and then your proof is much more general.
Yeah, we could try this.
And then biologists can find out which function is really there.
Yeah. Yeah, that's right. Yeah, so from this free energy, you can derive your equation, which is now this one. So if you look at the equation of N1, for example, you have this almost the same term than before here, divergence of N1 times gradient of P1. But P1 now is the pressure P plus N2 times the pressure Q. And it's the same for the other way around for N2. And we have this fourth order term here, which depends on the parameter alpha. Just to tell you, there is one special case if you consider that Q is equal to 0, so just P1 and P2 are equal to P, and that you have alpha equal to 0, so you don't have this fourth order term. Then the model became a lot easier. And you can observe there is some property we say that if you have an initial segregation, then it's going to preserve segregation. So this is nice. And we're trying to also do the work for this special case. But what we're interested here is really to have a model with initial overlapping between the species and see how we can create segregation between the species. So now we're trying to guess what's going to be the limit of this model. So we still have this equation because of the expression of the pressure, P. And so we still get the free boundary domain. So you have a domain where the total density is equal to 1 and outside the pressure is equal to 0. Then thanks to the expression of the pressure Q, you have this. So this term is converging to 1 plus R infinity Q infinity. And this term is converging toward Q infinity. Then these two terms cancel. And since Q infinity is strictly positive, bigger than 1, you can say that R infinity is going to be equal to 0. So you have the segregation in your limit model. Then what's going to be the limit equation of the density? Well, it's the same that in the one species case. You can rewrite the equation of the density under this form, where here you have a Laplacian of H, and here in H you have the same term than before for the pressure P, and this is the new term with the pressure Q. So then if you go to the limit for h, you have, you have this term which cancels, so you stay with p infinity, and then this term is going to r infinity, q infinity. This one is also going to q infinity and minus q infinity. So at the end you get p infinity. So the limit equation is going to be this one. Okay. And now we also want the behavior of the pressure inside the domain. So same as before, we take the equation for the density and you multiply it by p prime of n, and you get this equation. So you multiply by epsilon and you look at the limit when epsilon is going to 0, and you're going to stay with p squared times Laplacian of h, but h is going to p, so you're having Laplacian of p, which is equal to n1 g1 plus n2 g2 equal to 0. And then the speed of the boundary. So if you look at this equation, it's telling you that the density is moving with the velocity Laplacian gradient of p. But then since p is equal to p plus n2q, at the boundary of the domain, so either at the interface between the two species or at the boundary of the domain with the outside space, you're going to have this term which cancels, so you stay with p. So you're going to have a velocity of a boundary which is proportional to the gradient of the pressure, even if you're at the interface between the two domains. So I've made a new drawing so you can see what's going to be the limit model. So you have two space, one space where n1 is equal to 1, n2 is equal to 0, and one where n1 is equal to 0 and 2 is equal to 1. Inside this space, either Laplacian of p is going to be equal to minus g1 or minus g2. The boundary is moving with the velocity minus gradient of p, and the pressure outside is equal to 0. So now, showing this analytically is a lot more difficult than for the one species case, because here you don't even have a comparison principle in the equation I've shown you. And every time you try to find some a priori estimate, you're stuck with some term where you multiply the gradient of the product with the gradient of the total density, and this you don't know how to control it. So what we've done is that we've tried to show this numerically. So to be able to do simulation, if you remember, we have a fourth order term in our model. So this one is not easy to deal with. So we introduce a relaxation system where we have two new parameters, C1 and C2, and we replace the fourth order term by this term. So it just became the divergence of this. And then C1 and C2 are given by some Poisson equation. Nu is the relaxation parameter, and if nu is going to 0, then we are going to return to our initial model. So then to do the simulation, I'm just giving you quickly the scheme that we're using. So we do a time discretization where we use an explicit Euler method. Then we use a finite volume method in space, where basically, this is the classic one for a Laplacian term. And then we have a flux here. And the flux is is the flux, so it's n times the velocity. And just now, the velocity is not only the pressure P, it's the gradient of the pressure P, it's the gradient of the pressure P minus C minus N. Okay? So, and we take care of, in the scheme, knowing where come from the information. So if the velocity is negative, we are going to take the information for one side and way in the same in the other way. We have some CFL condition here, so that the density stay non-negative and also that the density stay below 1. Now I'm going to show you some simulation. So here what we are interesting here is to compare the model that I've just shown you. I'm going to call it the gradient flow model because it derived from the gradient flow, and the free boundary model. So in full line here, in red or in blue, you have the gradient flow model, and the cross are the free boundary model. So we can compute the solution of the free boundary model. We've done it with a simple case where you don't have segregation, where you have segregation at the beginning. So we just took two Heaviside functions, which are defined here. And then we suppose that the velocity of the red species is growing faster than the one of the blue species. And yeah, the parameter I took are epsilon equals 0.1, m equals 10. So these are not too small or too big. And we will see that we already have nice result, but it's a nice configuration. So, and we take alpha equals 0.01, so we have a small overlapping at the interface between the species, but it's not big, and nu need to be smaller than alpha, so we have this result. And when I'm going to start the simulation, you're going to have the pressure, which plot in black. So here what you can observe is that the two models are quite similar. You have the red species, which is going faster, so it's pushing the blue species to the side. And the pressure are almost the same, except to this region, where you see it's what I was telling you before. You have an interface between the two species here, so they can cross a little bit, and it results in this and the pressure. But otherwise, it's quite nice result. So it means that it was the good guess for the limit model. So now I was thinking that I could just show you a simulation with strong overlapping at the beginning, so you can see what is actually doing the model. So we start with two species, where here the red species is growing faster than the blue species, and we kept the same parameter than before. And you have this kind of dynamic. So you observe that quite quickly there is the creation of domain. So you really see this kind of free boundary domain, but you still have a bit of overlapping here, because the parameter epsilon and m that I took are not so, m is not so big, so you still have some overlapping, and it's going to be more difficult for one species to go out and to find its own space.
You're doing it in 1 dimension.
Yeah, right now, I mean, I've done some simulation in 2 dimensions, but right now it's in 1 dimension. Because to check the model on the free boundary model, it was easier to do it in 1 dimension. And
do you see eventually the second purple getting squeezed out completely?
it cannot be squeezed out, because you cannot destroy the species somewhere, it can just expand.
Do you see the solution of the heat equation in the domain?
It's not
What, sorry,
I have a lot of oscillations. Aren't you supposed to have a solution of the heat equation inside the domain, or was I wrong?
No, I don't think so.
Okay.
Maybe with one species, but okay. And so, so this is just a summary of what I present you. So a model with one species, and we've shown the limit to an Hele Shaw model. And then I present you a model with two species, which prevent mixing between the species, and we've checked numerically the convergence of this model. And so how can we use this kind of model? So the one species model can be used in any kind of tissue growth, and more specifically in cancer growth. Then the model with two kind of populations. So there is a lot of tissue in biology which have this kind of property, not only the imagine that described Drosophila. And you can also imagine that you're working with healthy tissues and cancerous tissue which are not mixing, and apply this to this kind of case. And then having the limit toward the free boundary model is helpful if you want to study the geometry of the tissue at the end. And the work to do is, we're trying to do the analytical proof for the case q equals 0, alpha equals 0, and then doing the model in 2D. So I've already had some work, some result on this. And then we want to introduce the stretching and the compression, because it was our initial plan. And thank you for your attention.
Thank you.
Yes.
Okay, no, maybe not to you. Yes.
How do you, let's say for this one-dimensional work,
Yes.
with two species, how do you test it? Can you test it on some obvious cases where you would know what to expect, and then compare your results with that?
So do you talk about just the model or the limit? Just the model. I guess we could do it. I mean, that's one of the plans, to really use this kind of model and to apply it. And we're working closely with a team like Jean-Paul Vincent, which is working at the Francis Crick Institute, and they have the plan to in 2D. I mean, so not in 1D. Yes, sorry. In 2D, they're going to take the disc and destroy some part of the tissue and see how it's growing back. So, for example, if you destroy a part of the hinge, so the surrounding part of the tissue, see how it's growing. So is it the pouch which is going to grow, take the place, or is it going the hinge which is going to reconstruct? Stuff like this.
Okay, Laurent, yeah.
Can this model also be applied the other way to loss of tissues, atrophy, or?
So what do you mean exactly? By
Instead of growth, like yeah.
well, yeah, I mean it's just assumption on the growth function, no?
So there's no problem going backwards.
Yeah, no, I don't think so.
Other questions? So do you have, I think I have more or less the same question about, so do we know how to, it may be not, because your question was about fitting parameters. Alright. It seems that we can have a lot of different behavior if we start from different initial values. Do we have some kind of ideas about what we can express with this kind of thing, what kind of model we have? Alright. I mean, okay, what I want to say is that with your simulation, you are pretty sure to understand what kind of thing you can generate with this kind of model, or you...
Can I reformulate your question?
Yeah, okay, thank you.
How sensitive are your results to the particular form of this function for the overlap of the n1 times n2?
Well, I didn't try with any other function than the pressure law that I show you, so I don't really know, but I guess it will do the same kind of result. Wow.
So we're checking.
Yeah. Well, it's easy to check. I just have to change few things in my.
Yeah, it's not up yet.
Yeah, because even when I'm to show the limit, the expression of q does not change a lot of things. So yeah, we could try with different expression.
Before I must say something. Are you interested more in the finite parameter situation or in the limit situation?
Well, we're interested in the two, because it's nice to have a model which imposes segregation in species, even without going to the limit. But then if we want to study the shape which is going to take the tissue, to compare with biological results, it may be useful to go to the limit.
Okay, thank you. Thank you.